here we go. Suppose f of 0 is equal to the number 3, and f prime of x is less or equal to 5 for all x. Question, how large can f of 2 possibly be? Alright, so here's an illustration. F of 0 equals negative 3. So you see that point in purple, that's the point in the graph. 0, comma, negative 3. Now, f prime of x is less than or equal to 5 for all x. So that means that for points on the graph, the slope of our tangent lines will never be higher than 5. So that should have some degree of control over the possible values of f of 2. So what's sort of the maximum value that f of 2 can take? All right. We're going to solve this problem by using the mean value theorem. Well, first off, does the function f satisfy the mean value theorem? And well, if we're going to use the mean value theorem, we're supposed to have an interval because we're given f of 0 and we're trying to analyze f of 2, then the natural interval to consider is the interval 0, 2. All right, so first off, is f continuous on the closed interval 0, 2, and is f differentiable on the open interval 0, 2? Well, the fact that we're able to make a comparison between f prime of x as being no greater than 5 necessitates the fact that f prime exists whatever the value of x is. Well, because if f prime does not exist at some value of 5, how can you compare it to 5? That would be impossible. So the fact that we're able to make this comparison means that f prime of x exists. F is differentiable for all x, therefore f is continuous for all values of x. And that is our justification for the conditions of the mean value theorem. F is continuous not just on R but on 0, 2, closed interval, and f is differentiable on the open interval 0, 2. Therefore, conclusion, there is some number c in the open interval 0, 2 such that f prime of c is equal to this, f of 2 minus f of 0 divided by 2 minus 0. Well, c is a number, and this left side involves f prime of c. Then we get to use this condition that consequently f prime of c is less or equal to 5. But f prime of c is this fraction, and therefore this fraction is less or equal to 5. Now, how that helps us is because we know the value of f of 0 is negative 3, so we get to plug that in, and voila, we have this inequality involving f of 2, the denominator is 2, multiply it to 5, we get 10, and then this is plus 3, so if you move it to the other side, you get 10 minus 3, that's 7. F of 2 is no greater than 7. So that's the answer to the question. How large can f of 2 possibly be? F of 2 can be no larger than 7. F of 2 is at most 7. And to convince us visually, graphically, why that has to be the case, consider from the point 0, negative 3, constructing this line, whose slope is no greater than 5. So imagine that you are a traveling point on the graph, you're at this position. Now the slope can be visualized as the direction and the speed that you're taking, but then you have blinders, you can't go higher than this line, so you could go somewhere else, like for example here. Alright, and then you see that small red segment that's parallel to the dotted line, so that small red segment has slope 5. So let's say at a future time you're at this location, you could go anywhere else here, moving forward to the right, as long as you don't go higher than this red segment. And suppose you ended up somewhere here, then you still can't go higher than that red segment. Then if you continue that, then you can't go higher than that. Okay, which happens to be the point with coordinates 2, 7. So in fact, you can verify from 0, negative 3, this point, all the way to this point. With coordinates 2, 7, the slope is 5. So, like, if you want to go as high as you could, the only way you have any hope of achieving that is if you were to remain on this particular straight path, but then clearly you cannot exceed the slope of 5 at any time, so that's as high as you can go. Alright, So the reason why this ties up with the previous velocity problem, I'm sorry, I wish I pointed it out while I was talking about the velocity problem, is how are we so sure that the truck at some point exceeded the speed limit of 60 miles per hour? I suppose the idea is that um, this truck was able to cover such a large distance at such a small amount of time. So even though nominally, if you look at the rates at when it passed the first patrol car and the second patrol car, even though the two rates are 50 miles per hour and 50 miles per hour, way below the speed limit of 60, but hey, that was too much distance covered in such a short amount of time that at some point this truck must have oversped and exceeded the speed limit. So the velocity, in a certain sense, has some degree of control over how far you could go. And we see that happening. We see that happen with this particular example. You can think of f prime of x as a way of controlling the velocity, how fast, what is the direction that our traveling point in the graph is taking. And so therefore, the value 2 seconds later, so to speak, can only be so much. In this case, no greater than 7. Right? I have another example for the mean value theorem, which you're going to see if, yikes, no. Okay, scroll up here. Oh, finally, this statement that was promised. F is continuous on the closed interval AB and differentiable on the open interval AB. So if f prime is positive for all x in AB, then f is increasing on that closed interval. And then second statement, if f prime is negative on the open interval AB, so for all x in that open interval, then f is decreasing on that closed interval. And then lastly, if f prime is 0 for all x in the open interval AB, consequently f is constant on the closed interval AB. I went ahead with applying this theorem to our optimization and graphing exercises, promising that at some point we're going to prove this. Well, the time is now. There are 3 statements. I'm going to go into the details of the proof of the first statement and then just describe to you how to modify the proof of the first statement to adapt it to the second and third statements. Okie dokie. F prime is positive. Let's assume that. Suppose f prime is positive for all x in the open interval AB, illustrated there on the right side. Now, what is it that we have to show? We have to show f is increasing, meaning if you draw the graph, it would have to be going up. How do we do that? Choose any two values, m and n, inside the open interval AB. So we should be able to change the values of m and n, so as long as they're there, and with n coming after m. So m less than n. So to show that f is increasing, what we have to do is show that the point on the graph corresponding to m would be lower than the point on the graph corresponding to n. So in other words, we have to show that the y-coordinate at n is higher than the y-coordinate at m. All right, so I'm moving the point corresponding to n. We have to show it's higher than the level of the point corresponding to m, so higher than that red dotted segment. All right. So we're going to use the mean value theorem. Notice that the conditions satisfied by f are precisely the conditions of the mean value theorem. So, however, we're going to apply the mean value theorem for the function f not on the closed interval AB, but on the closed interval mn. Why? Because if you look at the statement we're trying to prove, it involves not f of a and f of b, but instead f of m and f of n. All right, so house check verification. F is continuous on the closed interval AB, and mn is inside, so therefore f is continuous also on the closed interval mn. And then f is differentiable on the open interval AB, and the open interval mn is inside, so f is also differentiable here. So because the conditions of the MVT are satisfied, the conclusion follows. There is therefore some number c inside mn such that f prime of c is equal to, well, f of n minus f of m, the difference of the y coordinates corresponding to n and m, divided by the x coordinates themselves, their difference, n minus m. However, c being a number inside mn is therefore also inside ab. What are we assuming in this first statement? The derivative is positive for any number between a and b, such as the number c. So, okay, f prime of c is positive. How then are we going to use that? Let's look at this equation characterizing the number c. F prime of c is equal to that fraction, or equivalently, the numerator of the fraction f of n minus f of m is equal to f prime of c multiplied by n minus m. Now, we just pointed out that the first factor, f prime of c, is positive, but what about n minus m? Well, n is larger than m, so the second factor is positive. We're therefore multiplying two positive numbers, which means that their product is positive. But then that's f of n minus f of m. So in other words, f of n has to be greater than f of m. And that was precisely what we were trying to prove. So we've shown, therefore, that, hey, it doesn't matter how m and n are chosen inside the interval ab. It's always going to be true that the y-coordinate of the point n, which happens later, will always be higher than the y-coordinate of any point m, which happens way before that. So that's the proof of statement number 1. What about the proof of statement number 2 and also 3, which are proved similarly? The difference would be in statement number 2, f prime of c would be negative. And if f prime of c is negative, making this first factor negative, then the product would be negative because n minus m is still positive, with n coming much later than m. So what's going to happen is that f of n, instead of being bigger, would therefore be smaller. In other words, if you look at points here on the interval ab, for a point which happens much later, such as n, happening much later than m, the y-coordinate at n will be smaller than the y-coordinate at m. So that implies that the points on the graph will be on a decreasing trend. So the function f is decreasing. And then for the third statement, if f prime is always 0, so that means this first factor is always 0, so the product is 0, meaning f of n would always be equal to f of m. In other words, it doesn't matter how you choose m and n between a and b, the y-coordinates, the function values are all going to be the same. So in fact, what you could do is, say, take m to be a, and so then you get to show that, hey, no matter how n is chosen inside this interval, the function value at n will always be the same as the function value at a. In other words, all function values are the same. And so that's why f is constant. And that's the end. Thank you. Bye-bye.